Yeah, unfortunately, even LRU is not easy to implement. I mean, it's not to say that we cannot implement it, but in terms of hardware, that's still quite expensive. And last time we even looked at the one particular implementation. Let me show you that again. Just a second. So when we have a hash table and we have a double linked list. So let me go to the last. Yes, so that was the hash table and a double linked list. So the idea was here that we can use the hash table to access a corresponding block or page, depending on what the this used for. We can access it faster by just using a hash table and specifying the corresponding page number, so that we can have a fast pointer to the double linked list. So now the double linked list itself, why do we need it? Well, the reason for the double linked list is that whenever we access a corresponding page or block, depending on its file system or memory management, right, we would move the corresponding entity to the most recently used site. So now the other site is going to be least recently used, obviously, right? So therefore, you will maintain head and tail for the double linked list. You're going to, whenever you access, you're going to move it to the head. Whenever you want to kick out some page, you're going to look at the tail. So we don't have to use a double linked list. We can also just maintain some sort of timestamp when it was used. But the disadvantage of that is that we don't have an easy way to tell which page has to be kicked out. Specifically because we have to effectively scan the entire memory to detect which page can be, which page has this least recently used stamp. So yeah, anyway, there are some costs like computing a hash of page address anyway, and then in addition to this, either we have to maintain this double linked list, or we have to maintain timestamp and then scan this timestamp later. So obviously this cost is non-negligible. I mean, imagine if you have to just access 2 bytes, you have to do all these operations. For every memory access, you have to do that. So obviously that's not good. So can we do better? Well, yes, there is, for that reason, we have LRU approximation algorithm. So now LRU is an approximation of the optimal algorithm. So now we are trying to find, but that still is kind of complex. Even though now it's realistic to implement, it's still complex in terms of modern hardware. So, okay, so then we have to use an approximation of LRU effectively. So the idea here is that we're going to associate with each page a single bit called a reference bit. So remember that we have this reference bit in the page table entry. So now this is why it's actually useful. So this reference bit is going to keep track any memory access to that page. So it's set to 1 whenever page is referenced. So then a reference bit is cleared periodically at the course timescale. Maybe we have an interrupt handler which periodically going to clean that up. Clean them up, right? So, but some way we're going to clean them. So the LRU approximation, algorithm is called the clock algorithm, or is sometimes also called second chance algorithm. And there is also some variation you can look in Linux. I don't think they use the original clock algorithm, but they use some variations of that. So more elaborate algorithms, but nonetheless, I think this is something worthwhile to consider, right? So at least the basic algorithm, right, that should be used. So the idea here is that we're gonna keep frames in circle. So upon reference, bit set to 1. So once we reference the page first time, we're gonna set the bit to 1. So on a page fault, there are two possibilities. So if the bit is 0, then replace page and set bit to 1. Because once we replace the page, we reference the page, we set bit to 1. If bit is 1, then we are not going to attach this page. We're just going to attach the bit to 0 and then advance pointer to the next frame. So let's look. It may be a little bit confusing, but let's look at some example. So we keep frames in circle. So upon reference, bit set to 1. So on page fault, we're going to check, okay, if bit 0, then replace page and set bit to 1. If bit is 1, set bit to 0 and advance pointer to the next frame. So we have this reference string A, B, C, D, and so on, right? So let's say A, first time we brought A, there is a page fault, we set bit to 1. So, then we brought B, then we brought C, then we brought D. All of these bits are set to 1. We filled up the entire memory, we only have 4 frames, right? So now we get to the point where we have B. Okay, B is there. We don't have a page fault yet. So we just, reference this page, that's fine. There is no page fault. Then A, okay, that's also fine. It's already here. Then finally we have E. So this is where we're going to get the page fault. So our current pointer points to A because that's how we initialized initially, right? When we brought all these pages in and the initial state was that we point to A. Okay, so now A, you see, according to the algorithm, what should we do? If bit is 1, and it was 1, right? So it was previously 1. Set it to 0, and then advance pointer to the next frame. Okay? So, but we don't kick out the page yet. So we give it a sort of second chance for page A. So now we are going to page B. Okay, the same thing happens here. It was 1. We set it to 0 and then advance pointer to the next frame. Right? So now it points to C. So B is 1. Again, we switch to 0, move to the next frame. D, the same thing. So finally, we came back to A. So, and then you see, if bit is 0, replace page and set bit to 1. So that's exactly what happens. So because A was 0, so now we can finally replace it because we already went through the entire round. And then we found that, we already set bit from 1 to 0. So now page A has to be kicked out. So page A is kicked out and we bring page E and bit is set to 1. So now we have next page, F. The same thing, right? So B is already 0. So B is ready to be kicked out. So now we set it to, we kicked out B, set page F and reset B to 1, right? So, okay, then C. C has to be referenced. So C is not kicked out. So you see, C was 0 because of previous operation. But now because C was referenced, C is reset to 1. So we don't kick out C. So in fact, we kind of reset the counter to because page C was again accessed. So we cannot really kick it out, right? So we reset B to 1. So and finally, we have to go and replace we have to bring page G. So what do we do? Well, we go to page C, which was just referenced. And because bit was 1, we set it to 0, and then advance pointer to the next frame. So now D was 0, so that can be kicked out, and then we can replace this page. So you can check, right, and you can see that, for example, because C was accessed, this page C was accessed, it was not kicked out, right? But the page D was kicked out instead. So it's an approximation. So you can, it's of course not going to be least recently used. It's an approximation. But I guess it's a good approximation to some extent, right? So something that should be close. Any questions about this algorithm? So we go, we give a second chance to each page. So initially each page has a bit 1 when we bring it. So whenever we try to choose the victim page, we don't kick out this page right away, just like, I mean, when we do with FIFO, right? So you can see some similarities maybe with FIFO partially, because we also have this pointer going back and forth, right? But we give a second chance to that page. So we don't kick it out right away. So only when we see that we went through the entire round of all pages, and now this page still has reference bit to set to 0, that means it was not accessed in the meantime. So that means we will kick it out whenever we choose a page. And again, the page that we want to kick out, that's going to be determined by the pointer. So only when the pointer reaches us, then we have to evict that page and bring something else. Yeah, take a look one more time at the slide if you are confused, but I think it should be very much straightforward. Just follow that rule. If bit is 0, replace page and set bit to 1. If bit is 1, set bit to 0 and advance the pointer to the next frame. So there is some variations that we can do. For example, we have also the dirty bit. So maybe we don't want to kick out a page which has to be written to the disk. So then we may want to kick out a page that doesn't have to be written. So that means the dirty bit is set to 0. So it's not just reference bit is 0, but dirty bit, that means it was not written. Because if it has been written, I have to go and replace that page. And that means I have to have an additional write operation. So what is the advantage of dirty bit of kicking out the page with dirty bit 0 versus dirty bit 1? Let's check how you follow it. What is the advantage of that? Any guesses? I think you wanted to say something now. I'm sorry? Yeah, so we don't need to write it. So that means whenever we need to bring it again, we just need to read it, as opposed to writing and then reading. So at least we have one less disk operation. And very often writing is also slower than reading, right? At least for SSDs, maybe. I don't know for hard disks, but for hard disk, I guess everything is slow. But you certainly there is some advantage of not writing. So that is one variation that we can use. So we can use both reference and dirty bit to determine which page we need to kick out. So another variant is least frequently used. So we talked about least recently used. And it's probably a good approximation of the optimal algorithm. But there is another approach, least frequently used. So let's look at this algorithm as well. Okay, list frequently used. So let's go back to our original string that we looked at last time. Let me. Yeah, so let me write it down. 1, 2, 3, 4. 1, 2, 5. 1, 2, 3, 4, 5. So obviously, I mean, remember that we have just 4 frames. Obviously, the first, first 4 axes are going to generate page faults. 1, 2, 3, 4. So then, what do we have? We have 1. Okay. So now let's say the counter. So what for least frequently used, we will use a counter. So previously, let's say it was just 1, right? Let me put counter 1. So now we access 1 again. So that's going to be 2. Then we access 2. That's going to be 2. Then we access 5. Okay, so what do we do for 5? We need to kick out some page. Which of them is least frequently used? Well, we have 2 pages that are least frequently used, 3 and 4. But I guess we can break a tie by maybe some, page address or something like this, just like we did it for the optimal algorithm. So we can kick out this one and put 5 here. So 5 is going to be accessed just once, right? And then 4 still accessed once, right? Okay. So then we have 1, 2. Okay, 1 is free. 2 is free. 3. So which page we need to kick out? Well, again, they are kind of in the same situation. Both 4 and 5 are in the same situation. So again, we're gonna break the tie by kicking out 5. So we're gonna bring 3 again. And then okay, so we have 4 and 5. Okay, 4 now is going to be 2. And then we finally get 5. Well, again, we need to kick out 3 because that's least frequently used. So how many page faults we had? We had initial 4 page faults. Then we have 5, 6, 7. 7 page faults. So actually, in this particular example, I think it's actually even better than least recently used, right? So let's check that. In least recently used, we had how many page faults we had? I think we had 1, 2. Yeah, we had I think yes. So we had 8 page faults in least recently used, and we had 6 page faults in the optimal algorithm. So in least frequently used, we got just 7 page faults, right? So somewhere in the middle, right? It doesn't have to be like this. It doesn't necessarily mean that in every single case it's going to be better than least recently used. It's just this in this particular example. So what is the advantage of least frequently used? So tracking is simpler than in LRU, right? But what is the disadvantage? Well, the frequent pages may not be reused soon. That's the disadvantage. Just because the page is accessed, was accessed for a while, maybe we had a lot of accesses to that page, doesn't maybe at some point, okay, we access that page, we are done with that function, and we are never we're going to execute it again, right? Like imagine you executed some code maybe like 1 million times, and how long it will take to kick out that page even though it's no longer used. so it's definitely you can come up as an example where it's going to be worse than LRU. And I think LRU is still better approximation of the optimal algorithm, even though it's in this particular example, maybe it's worse, right? Okay, go ahead. Well, the clock algorithm, you see, it's only has one bit. So it's kind of like, well, what I mean, it approximates, right, the LRU, right? But the problem is it's not gonna match all the time, right? So, so it's for example, in LRU, we actually maintain the entire history, how far away that page was, right? So, for example, page A was, is timestamp 4, and maybe page B was with timestamp 700 or something like this. And based on this, we can say, when it was actually accessed to. Here, yeah, we have this pointer that is moving around, but there is no difference fundamentally between, like, say, B, C, and D. They all can be kicked out just because the pointer happens to point to them, and the pointer points in a sort of FIFO order, right? So therefore, it's kind of hybrid, like a FIFO with with some LRU behavior. I would say that, right? So there, I mean, you can look at the specific example, I guess. Let's maybe take it offline, right? But it's definitely not going to be the same. So, so what are the effects of high multi-programming? Well, once the degree of multi-programming is increasing and when we have a lot of processes running our system, then at some point, if we run out of memory, we should expect that, so we will have some thrashing, right? And, so at some point, it may, be not worthwhile, right, to do that. Depends on how much memory you have. Like, depends on how processes you run, how CPU intensive they are, so, and maybe, they're not using too much memory, they're only CPU intensive. That's also happens. But, so remember that there is a so-called phenomena like called thrashing. So when we have to bring back and forth, right? Let's imagine, like, here we bring 3 5 3 5. I mean, it's still okay here because we still have some additional physical frames. But imagine if, like, that happens for every single axis. You just, keep kicking out some page, bring some other page, kicking out this page, bring. I mean, at that point, your performance is basically degrading to the secondary storage performance, right? So, and therefore, it's not going to be great. So, okay, so this is a kind of exercise for you. Just, I mean, for the optimal algorithm, you can go through those at home and just take a look how many page faults we're gonna have in OPT, LRU, just for you. Take a look at home. So let's wrap up this topic, the page replacement algorithm. And so this slide we have already looked at. So that was regarding the LRU and hash tables. And let's talk a little bit about the project also, right? So there was some still questions people ask, and one specific question I think I got. I mean, I think we have covered, everything, like food optimization. But if you still have doubts about food optimization, please, feel free to ask me. Do we need to cover food optimization again? Okay. So just want to also remind you, because somebody I think asked explicit lists. you know, they only keep track of 3 blocks. So you remember that. Okay, go ahead.
It's just like when I'm trying to create a block, I'm not sure how to get the when the business block is added.
Okay, we'll check. We'll talk one more time, right? Just give me 1 second. Yeah, okay. So for explicit list, just to you know, just to remind you, for explicit list, we only keep track of 3 blocks. So how you keep the explicit list, it's up to you. For example, I suggested to you last time to create struct node, and that struct node will have previous and next pointer. And that struct node will be placed in the payload area of free block. So that means next and previous are going to point to the payload of the next block. If you don't want to point to the payload, you can point to the header. It's up to you. But I just thought that maybe pointing to the payload is easier because you can have the previous and next pointer, you know, kind of isolated in a separate structure, which is completely separate from header. And one thing that you have to keep in mind, previous and next, you don't keep in allocated blocks. It's only in free blocks. So for segregated list, you have an array of explicit lists. And each list supports a sort of range of sizes. And I suggested to use log2 function, and we're going to look at log2 function one more time right now. If you want to use segregated list, it's fine. So I heard that, you know, maybe at this point, if you're running out of time, or, you know, maybe if you maxed out the throughput with the explicit list, but you're still not doing that great in the utilization, maybe prioritize food optimization first. Again, because you know, so that's gonna probably give you more points. And you know, I heard that explicit list and food optimization are already gonna give you 100% points. I mean, I haven't verified that myself, but I heard that. Yeah, so segregated list and food optimization definitely gonna give you 100 points. 100% points. Just explicitly, it's unlikely. You know, explicit list, I mean, just segregated list will probably bring it closer to 100, but not 100. So it's still going to be like 92 or 95% or something like that. So it's up to you what you're going to choose. But I guess maybe if you want to get the highest number of points and you understand all these approaches, maybe prioritize explicit list first and then do food optimization second. And if you have time, you can also take a look at segregated list. If you don't know how to do food optimization, but still get less than 90%, you know, then you can also experiment with segregated list. It's up to you. Okay, let me show you the slides. So I already covered the log2 function for explicit list, but yeah. So but one thing that we haven't looked at yet. Give me 1 second. No, I mean, we have looked, I think, at this entirely last time, but I guess one thing that maybe some of you have missed that lecture and that was somewhere in the recording. So I just want to remind that function. So because maybe you didn't have that slide, because I want to put that slide after this lecture. So I think we already looked at this some time ago, how to implement log2. And I said, don't use the log2 from the C library because that uses floating point numbers. Use this log2 that calculates integers. So the way that you can use it, you can just, you know, you can use the built-in count leading zeros. Remember that count leading zeros counts counts leading bits which has value of 0, right? So if you have a binary 0, 0, 0, 1, 1, 1, 0, 1. Count leading 0 is going to return 3. So if you have 1, 1, 1, 1, 0, whatever, right? The count leading 0 is going to return 0. So let's look at this number, where count leading 0 returns 0. That looks like the number which is clearly higher than 2 to the power 63. So it's greater than 2 to the power 63 because it has upper bit set to 1. And and certainly it's greater, I guess, or equals than 2 to the power 63. So how do we calculate this? We have to subtract, so 64, this is size of size t is going to be 8 in our case, multiplied by 8, 64 bit. 64 bit minus 1, 63. And then it says XOR 0, which is going to be 63, right? I will get to that XOR. I think I have shown you with the subtraction operation last time, and this is with XOR. It doesn't matter whether we're going to use XOR or subtraction here. Just one of those examples where it wouldn't matter. Yeah, so we have 63. And if I do log 2 of this, I'm going to get 63 as the result, because 63 XOR count leading 0, 0 is going to be 63. You can test if it's 0, that means it's 2 to the power 62, then it's going to return 62. So it's going to be 63, sorry, 63 XOR 1. What is 63 XOR 1? So that's going to be F. Well, I mean, we don't need to look at the upper hexadecimal. That's going to stay the same. But let's look at the second hexadecimal. We're going to be 1, 1, 1, 1 XOR 1, right? That's going to be 0, 1, 1, 1. So that's going to be effectively one less, right? So it's going to get 62. We can check it because it's going to be one less. It was 1, 1, 1, and then it became 0. So it doesn't matter whether you subtract or do XOR in this case. So it's going to be the same. You can also instead of XOR do subtraction. So okay, so that is the idea. So basically, leading 0 is sort of kind of not the opposite of log 2, but kind of if you count it from the opposite direction, right? So that is what count. This is how count leading zeros and log 2 are different. So you can easily convert one operation to the other. So just use this, and count leading zeros is the instruction that we have in all modern CPUs. I think most architectures have that. Maybe not all, but most of them have it. And even if they don't have it, the compiler will replace it with the somewhat optimal approach for that particular architecture. So it's that in that sense it's useful to rely on that. So you can test it. You can run int main and check what log 2 of 1, log 2 of 7, 8, and so on. So if you run this program, we're going to get log 2 of 1. It's going to be 0. 2 to the power 0 is 1. Then log 2 of 7 is going to be 2 to the power 2 is 4. So it's kind of it didn't reach the class 8 yet. So that's going to be where 7 is now. But now log 2 8, 2 to the power 3 is 8. So that's the next class. So this is why it's going to be 3. And then you can test, the highest number that we have, highest integer is going to be 63. So it's going to go from 0 to 63. So I already gave you some time ago, I think, in this function, but we didn't have put it in the slide. So I'm putting it on the slide in case if you want to implement segregated list. Or in case if you already use some other log2 function, you can just replace it with this. Or if it works fine, you know, you can keep things as is. Just a suggestion to use that function. So other things, I don't think you will necessarily need it, but you know, just in case if you were wondering, you can also do some tricks. How do you determine that a number is a power of 2? Well, I mean, you don't need it for this project, by the way, right? So in general, probably you still need it. But you know, maybe you want to still optimize something. I don't know what, because what kind of allocator you implement, and maybe you want to optimize something for power of 2. Probably it's not worthwhile. It's better to do, you know, just optimizations that we talked about. But you know, so how do we determine if the number is power of 2? So we have value bitwise end value minus 1, and then we compare it to 0, right? So if that bitwise is 0. So why is it going to work? So how do we check if it's a power of 2?
If it's a power of 2, you'll only have a single one, sort of like
Yes.
as far left. As
Yeah,
you
like
can
this,
go.
right? Like this, right?
And when you subtract 1,
That's going to be
basically
0,
everything gets
1, 1, 1, 1, right? So and then we do bitwise, it's still going to get us zeros, right? But if you check with any other not power of 2 number, that's not going to be the case. There will be some non-zero value. Well, I think there might be some exception for 0, or so 0 is not, I guess 0 is not a power of 2 number, right? So, but let's not talk about that exception. Anyway, yeah, so, but for other numbers, it's going to be fine. Yeah, so, okay. So except zeros, I think it should be fine. So how do we determine next power of 2? Well, that's a little bit tricky, and I will not go into too much detail about this because I'll just give you a reference if you're curious. So, but the idea is that we will subtract value, and then we'll do this bitwise OR operations. So we'll shift by 1, then shift by 4, then we shift. Oh, sorry, we shift by 2, then we shift by 4, and you know, so on. So if it's 64-bit number, we're gonna go up to 32. I mean, if it was like 32-bit number, we would go only up to 16. So it just depends what the bit size is. And then finally increment it again, right? So why that's going to work? It's probably going to take a little more time to explain. But that's the function. That's a classical way to get you know, to approximate to the next power of 2 function, to the next power of 2 number. So you may wonder, you know, where you can read about this stuff. So I just put a link. So this is like this, and other things you can read on this web page. So there is a lot of this so-called bit hacks or whatever it is, right? So there is certain approaches where you can, you know, you can just do some tricks with bits, and you like we determine if the number is power of 2. It's a nice trick, and it works, and it's cheap, right? And therefore, you know, a lot of tricks like this, for example, that web page also describes how to implement count and leading zeros efficiently if you don't have the corresponding instruction. So there is multiple ways to do that. Okay, let me actually, I'll probably also want to talk about dual mode, you know, clarification. I want to clarify that a little bit. And I also want to revisit project 2, because in project 2 slides, I think not everyone was present, and I think we look at the last page, like last slide. I want to still revisit that one more time because project 2 is coming up. Let's make sure you have all the information you need to get started. So regarding dual mode, I think I already also mentioned that, but just wanted to let you know the textbook is telling you that you have a per process kernel stack. Well, first of all, that's I should say it's per thread kernel stack. It's not even per process. But you know, we haven't talked about threads yet. So when we talked about this, I think it will become more clear why. But you know, so that's just one minor detail. But another detail is that in terms of the hardware, there is no processes or threads or any task like this unless you use hardware context switching. So in the past, x86 would support hardware context switching. So you could potentially switch between, you know, you can potentially ask CPU to save and restore all registers. So it's not that great because you may have better control of what registers you need to save and restore, and therefore software context switch are much more preferred. And not to mention that RISC processors, they would not want to implement anything like hardware context switches because they're really trying to be minimalistic. So this function, this hardware context switch functionality was kind of disabled in x86-64 in 64-bit mode. So we only have software context switches. And as far as I know, neither Linux or Windows have ever used hardware context switching, even for 32-bit mode. But I think if you read the textbook, you kind of have the impression, I mean, of course, the textbook doesn't fully clarify this, but I think you have that impression that it's a hardware context switch because everything is saved and restored, all this registers saved and restored, which actually doesn't happen. You only save some registers, and but all other registers are saved and restored in the interrupt handler or trap handler. But still the CPU has that per CPU kernel stack because that's something that we have to have because there is no choice. We cannot run and use a stack no matter what. So we have to use this per CPU kernel stack. But per CPU kernel stack, like, I mean, may have like 16 cores on my computer. So I'm gonna have 16 per CPU kernel stacks. But you know, maybe I have hundreds of processes. So per process, I still need to have some per process kernel stack. So the way that it works is that if you look at some Linux code, or it will adjust this hardware structure to the corresponding per process kernel stack. So yeah, so it's per CPU in terms of the hardware, but in terms of the operating system, it adjusted to the current process. So it's going to select, okay, this process is running on this CPU currently, let me use that kernel stack. So this is how you use per process kernel stack. So if you look at this code, which kind of be a little bit scary, like in Linux, but if you look at this assembly code, for example, you can see that ESP0, this is where you specify to the hardware this per CPU kernel stack. This is actually substituted with the EBX value, and EBX register contained added on the previous line address for the top of the next task kernel stack. So that was the per task or per process kernel stack, and this is where you write it to this hardware structure whenever you switch from one task to another. So you know, there is no contradiction, but I just wanted to clarify that, you know, the reality is a little bit more nuanced than what the textbook describes. So you have hardware supports per CPU kernel stacks, but the operating system has to also support per process kernel stacks. Okay, go ahead.
So where do the per process kernel stacks go when they're not in use?
Well, if they're not used, I mean, you just have to create for each process a kernel stack. So whenever this process is started, you have to create a kernel stack, and to each thread, to be more precise, not just process. because you don't know. Let's say, let me give you an example. You are executing a system call, so you need kernel stack. But then while you're executing a system call, Linux supports preemption. So your task is completely preempted. So now next task wants to execute on the same CPU. On the same CPU. It cannot use the same kernel stack for that CPU. It has to use per process or per task kernel stack, right? Because the other task was preempted. That means it was stopped somewhere in the middle. So as soon as you have this preemption, then you have to maintain separate stacks. So if the kernel does not support kernel mode preemption, that is also, I think, possible in Linux to disable kernel mode preemption. Then it's fine to have just per CPU kernel stack. But if as soon as you support preemption inside the kernel, which is nowadays, I think, enabled by default, then you have to adjust that. So because now you have more stacks. Not just like, I mean, for every process you have a kernel stack, not just for every CPU. So does it make sense? Okay, so last time, so this is regarding the project, and I'm probably going to switch to that slide in a moment. I still have a couple of slides regarding the page table. So last time we looked at this 48-bit paging. So you have, remember that you have physical page offset. This is from 0 to 11 bits on x86-64. I think that was it the last lecture or the lecture before? I think I think it was last lecture, because we wanted to use the page table as the, no, I think it was, no, not the last, the lecture before that. Yeah, so we looked at this x86-64. So I just want to reiterate this one more time, because project 2 is coming up. So now we have a real page table, real architecture. So in this particular architecture, we have 12 bits for a page offset. So that means each page is 4 kilobyte. 2 to the power of 12 is 4 kilobyte. So now in 48-bit paging, like last time I explained how we do the sign extension from 48 to 63rd bit. So that's just a minor detail. Fundamentally we still have 48 bits. So just, minor detail that it's not 0 extended but sign extended. Take a look at that lecture if you like. I mean, I will not go over that again, right? So just take a look at that if you are confused. But the important thing that at every level we have 9 bits. So we have 4 levels, and at every level we have 9 bits. So 48 minus 12, that's going to be 36. So 36 bits we have to translate, and why is it at every level we have 9 bits? Well, because we have entry size of 8 bytes, 2 to the power of 3, and the page size is 2 to the power of 12. So 12 minus 3, 9, right? So we have 9 bits at every level. So now if we divide 36 by 9, clearly we get 4, right? So, and then this is how we get 4 levels, right? So this is 4 levels. So, and then there is CR3 register. This is special CPU register which loads the base address of the page table. So it's gonna point to the PML4 address, so the top level of the page table. Again, this was something that we use different convention. We called it level 1, but in x86-64 it's the opposite. They call it level 4. So it's just just a convention. As long as you clarify it clearly, that should be fine. So level 4, or the last level, so the top level is loaded to CR3. So just for your information, that's not something that you need for the project, but just to give you some idea what's happening recently, we have a 57-bit effectively virtual addresses nowadays because they introduced the 5th level. So they reduced the sign extended part and they introduced another level. So now you have 9 extra bits. So it was 48. Sorry, is it? Yes, 48 and now plus 9 is going to be 57. So 57 bit. I mean, potentially in the future, they can probably go all the way to 64 bit. They can just, I guess they won't be able to use it entirely, but at least, half of that page, they can still have the 6th level for 64-bit virtual addresses. I mean, something that they can do in the future, but they haven't done it yet. Or maybe they will never do it. Who knows? Okay, go ahead.
Are the numbers at the bottom the total virtual address space? Or are they like how much,
You mean 57?
like the 120 petabytes or the 256 terabytes?
Yeah, so that's kind of how much memory you can address at each level, right? So if you have 512 entries at the lowest level, right? You can address 2 megabytes. So this is 1, 2, 3, 4, 5, right? So the first level gives you 2 megabytes. Second level, it gives you 1 gigabyte. Then another level gives you 512 gigabytes, then another 256 terabytes, and then 128 petabytes. Because each level you kind of multiply by 512. 2 to the power of 9 is going to be 512. So 512 entries. Each entry is 8 byte. Okay, let me just before we wrap up our lecture, let me just open that. Give me 1 second. Let me open that. Oh, by the way, just let me show one more thing. Just give me 1 second before I close that slide. Oh, where's it off? Wow. For some reason, I'm disconnected. Okay, so one thing that we can also do is to run a cat proc CPU info. So if you do that, you will find that, for example, in my computer, it says 39 bits physical. So remember, 52 bits at most you can have, but they said in practice, it can be less than 52 bits. And that's what happens on my computer, for example, and probably on yours as well. It says 39 bits physical because there's no point to have more bits for the physical address. I don't have that much RAM in my motherboard anyway. Yeah, so that means other bits should be set to 0. But then it says 40 bits virtual, 48 bits virtual. So this is how you can test what your CPU has. I mean, assuming that you have x86 64. Just a second. And last time, okay, just why is it closed? Just wanted to show one last thing. When we talked about the project too, I just want to take a look at this example one more time, how we initialized for 4 GB address space. Okay, okay, just a second. Let me show screen. Presentation. So how do we initialize 4 GB of RAM? So for 4 GB, we need to reference approximately 1 million physical pages. So how do we get this? Well, because we have 4 KB, right, page, and if you multiply it by this, we get 4 GB. This is how we get this number, right? So approximately 1 million, right? I mean, you can calculate the exact number. So remember that at each level we have 512 entries, 2 to the power of 9. So this 1 million is basically 2 to the power of 20, right? 2 to the power of 20 divided by 2 to the power of 9, that's going to be 2 to the power 11, and 2 to the power 11 is 2048. So that means we have 2048 pages at the second level. Where is this picture? Yeah, so the second. So at the PDE level, we have, we refer 1 million pages. That means we approximately have 1 million entries. That means we have 2048 pages at the level 1, because each page contains 512 entries. So from level 2, we have to reference these pages of the level 1. So that means we have to have 2048 entries in level 2. So what does that mean? We have 512 entries in each page. That means we have 4 pages at the level 2. So that for PDE, for page directory, for the second level, we have 4 pages. Then finally, for the next level, we just need 1 page, and for the final level, we also need 1 page. So how do we do that? Let's say we want to create an identity page table. We iterate from 0 to this number, right, to the power of 20 minus 1. And then we're gonna effectively initialize the page address from 0, 1, 2, 3, and so on. If you want to create an identical physical identity physical page, I mean identity page table, that means physical page number is the same as virtual page number. So just for the sake of this example, right? In the project 2, I won't make it, at least the first half will not be complicated. You just need to create an identity page. So that means it's going to be virtual page number is the same as physical page number. So the current virtual page number is from 0 to 1 million, right? So in the same, you're going to put to the physical page number field. So it's going to be exactly the same thing. So just put this I in this initialization, right? And then also initialize bits and so on. So when you go to the second level, now this page number is different, because now we have to refer to the page of the first level, not the physical page that we are mapping, but the page of the first level. So how do we do that? Well, you can just have the starting address, which is the P address, plus 512 multiplied by J, and J is just the effectively the page number. You get this address, right? and then you shift it by 12. So by the way, here 512 by yeah, so each page table entry is 8, right? So this is why it's 512. So this is adjusted to this pointer size because each pointer size is 8 byte. I mean, each pointer points to the entry of 8 bytes. So this is why it's 512. So you got this address, but remember that you need to put the page address. So because our virtual and physical addresses are the same, we can just take this virtual address and directly convert it to the physical address and then shift it by 12 bits. So this is how we're going to get the PTE page address. And the same you're going to do for the next level and the level that's going to fall, right? So just remember that last 2 levels, they're not going to have their page filled up with everything, right? So you have to put unused entries with initialize them with zeros. Does make sense? So never put any garbage in the page table because garbage can be interpreted by the CPU that you are using some unsupported bit. So you have to initialize to 0 any entry that you don't use. So obviously you cannot reference less than 1 page. So if you just use first entry of that page, initialize this first entry, but everything else, like 511 entries, should be initialized to 0. Yeah, take a look at the slide when you implement it. I think it should be more or less clear once you look at this calculations. Yeah, that's it for today. I'll put slides on Canvas after the lecture.